Welcome to my YouTube channel. In this video we are going to be looking at a practical application of the one-dimensional diffusion equation, part 2. So a typical problem that can be solved using the diffusion equation is given below. So from this question, if both the ends of the bar of length L are of temperature 0 and the initial temperature is to be a prescribed function f of x in the bar, then find the temperature at the subsequent time. In this problem, we can see that the temperature at any point in the bar of length L is time dependent. That's why we're asked to find the temperature at the subsequent time t, right? So, and because the temperature will definitely diffuse from one point to another when it is heated and withdrawn from the heat source. So the best equation to solve this problem is definitely going to be the diffusion equation, and because it has a length of L, no breadth, no height, then it's going to be a one-dimensional problem. So this is the diffusion equation that is needed to solve this particular problem, where our file here is the temperature at any point, x is the position, t is the time, h is the diffusivity constants, right? So we assume that our file is a function of x and t. From this expression, from this question, we can bring out the boundary value problem for this particular equation, and that is the fact that from here, if both the ends of the bar of length are at temperature 0, so if we assume that the beginning of the length of the rod bar is 0 while the end is L, that means if this x is 0, the temperature there will be 0. So that leads to this one. So we are saying that if both the ends of the bar of length are at temperature 0, so at x equal to 0, the temperature is 0. Then also at x equal to L, at x equal to L, that's the other end, then this temperature will also be 0. That leads to this one. This is second boundary condition. Boundary conditions. These are boundary conditions. Then finally, we were told that and the initial temperature is to be a prescribed function f of x. So what that means from here, from this, is that if t is initial, that means at 0, this temperature will be equal to f of x, which is a prescribed function. So that gives us this xyl at x anywhere in the rod, but the initial temperature, the initial temperature is f of x, where our x runs from 0 to L, right? Now, if these are the necessary boundary conditions, to solve this particular problem, we must first of all find out the generalized solution of this particular expression, which has been solved in part 1 of this channel, right? So without solving this, the solution to this, you can always fall back to the part 1 of this video. You'll see how the solution is derived. So the solution to this is given as psi x comma t equal to this expression. So from this expression, our aim is to determine the value of a, k, b, and c. These are constants to be determined using the necessary boundary conditions. Okay, but if you notice from this equation, c can go in here and here, so that ac can also be given as another constant called a. BC can also be given as another, can also be written as another constant b. So that reduces to this. So if you notice, we had 3 boundary conditions, and from here we have 1, 2, and 3 constants to be determined. 1, 2, 3. So with 3 boundary conditions, we can calculate, or we can find the 3 constants. So let's start with the initial, the first boundary condition, which is at x equal to 0, the temperature is 0. So wherever we see x in this equation, we put 0, and everything here will now be equal to 0. And so that leads to this expression. So at psi of 0 comma t, it must be equal to 0. So wherever I see our x, we'll put 0, because this expression can also be rewritten as this expression here, right? So our e is already in, our c has already been taken care of by this b, our c has already been taken care of by b. So this expression can also be expressed as this. So we put our x equal to 0, our x equal to 0, then leaving this part since there are no x part here. Now if we simplify this, you realize that sine kx, sine 0 is 0, cos 0 is 1, leaving only a, and that gives us a cos 0. This part is divided by this part, so leaving only this inner part, and this one will also reduce to a plus 0 because everything here will be 0. Now if a plus 0 is 0, that means a equal to 0, and that leads to a equal to 0. Now that we have found a equal to 0, they will now go back to this original expression, and wherever we see our a, we'll replace with what? 0. Then we'll come back with psi file of x comma t. So if we put a equals to 0, this equation, this part will no longer exist, but this one will exist, and this will now be the new expression that will start our solving from. And next condition, you can see that after applying the first condition, boundary condition, we're able to show that a equal to 0. So the next boundary condition is to show is when x equal to L, everything will be equal to 0, and in so doing, wherever we see x, put L, then everything will be equal to 0. So that will be this expression, file of L comma t equal to 0, which is equal to this expression. Now if we are rearranged, we'll have something of this form. Now from this point, we notice that we have b times this part equal to 0. B can never be equal to 0. This part can never be equal to 0. And why is it so? If b is equal to 0, that means this file of x comma t will cease to exist, because a can never be 0 and b will be equal to 0. That equation will not exist. And this part, if this part is 0, this part multiplying the entire expression will also be equal to 0. So since this part can never be 0, this part can never be 0, therefore this part must be equal to 0, and that leads to this part here. Now from this expression, we can tell that there are certain parameters, there are certain values that this expression will take that will make this one be satisfied. And one of them is when this part is 0. So sine 0 is 0. Another one is pi. Sine pi is 0. Another one is 2 pi. So sine 2 pi is 0. You can also check sine 3 pi is 0. So if you continue, you discover that that's this KL will definitely be equal to n pi, where n runs from 0 to infinity. So if KL is equal to n pi, that means this expression will be satisfied. So that leads to KL equal to n pi. So since we are looking for k, if we make k the survey formula, we'll have this expression. So you can see with this next condition, second condition, we're able to show that k equal to n pi all over L. So we can now substitute this one back into this expression, and that gives us this. Although we'll come back and substitute into these parts towards the ending, but for now let's skip this one, but we can substitute it here. So this is our expression. So finally we are left with one expression here, b of n. Now what you notice is that we have summation, then we have b subscript n, and the reason why it's so is because of this n here. For every value of n, there is a corresponding value of b. So we can say when n is 0, there is a b naught corresponding to that value, which satisfies this equation. When n is 1, there is a corresponding b1, which also satisfies this equation. So by the time you sum all this expression for b1, b2, that leads to this summation sign here, right? So at the end of the day, we can now say what is left is this bn, which is the last constant to be determined, and to determine it, we'll invoke the last boundary condition, which is at t equal to 0, everything here will be a prescribed function f of x. So wherever we see t in this expression, we'll put 0, and that leads to psi t equal to 0 equal to f of x equal to this part. So t multiplied by this will give us 0, and you can tell that this one is equal to 1, which reduces to this part here. Okay, so from this point, the best way to calculate, to make Bn the subject formula, because our aim is to make Bn the subject formula, or to solve for Bn. The best way to solve for Bn, or making it stand alone, is to multiply both sides by sine n pi x all over L, and integrate both sides from 0 to L. In so doing, we will eliminate this one and make B stand alone. So let's see what happens. So we multiply sine pi to both sides and integrate from 0 to L. So sine pi here, sine pi, this part becomes squared. So from this point, we can leave these parts and focus on these parts. If we integrate, because this b of n and summation can be re-expressed by bringing it out, and that gives us this one here. If we integrate this one with respect to the x, right? Although we are not going to show the working here, but if you integrate this one from your elementary mathematics, you can show that everything here will be equal to L over 2. L over 2. I wish I have enough time to show that part. So it will be L over 2, and that leads to summation of b of n L over 2, this part here. Okay, now we have for b0, anytime you see 0 here, that b0 will be equal to this part. We have for b1, anytime you see n here, you put b1, right? We have b2, you also have, anytime you put 2. So that's the expression for, so there won't be need for this summation again, because we are now saying for a particular b of n, this is what happens, right? So there will be no need for this summation sign again, and that leads to this expression. So from here, by making our Bn the subject formula, 2 comes here, L goes under, and we have this expression. So finally, we have made our b of n the subject formula, following that manipulation that we made. Then we can now finally substitute b of n as this expression into that original equation. So, and that gives us b of n 2 over L 0L f of x n pi L, right? And we get our file, which is x of t summation of 2 over L. This part is the Bn part times sine n pi over x times exponential. So if we rearrange these parts, then we'll have, by sending this one, so that this part alone, the integral, it's only this part here that are inside the integral, so we can take them forward, and that will give us these parts. So our k now has now been replaced by the expression, the original expression that was determined, and this is our psi of x of t, which is the entire equation. Once f of x has a real value, like maybe a number, maybe 1 or x, then we can further integrate this one and get the real expression for this. Our f of x can be sine n pi x all over L, and by the time we integrate, this part will become L over 2, and that further simplifies this one. So our f of x can take any value, which is a function of x, or probably even if it can also be 1. So that's all for this video. I hope this helps. Please like, share and subscribe to my YouTube channel. Thank you.